Good day, class. I am Mr. Adeyeye Adelu Peter. So I'm going to be taking us through these miscellaneous examples. So please stay tuned. So this is one of the examples I'm going to be solving for us today. The question says, a particle undergoes an oscillation between x and y as shown in the figure below. Anyway, figure beside, this is a figure they are talking about. X and y are at the 20 centimeter mark and 60 centimeter mark on the meter rule respectively. Full stop. The particle takes 4.0 seconds to move from x to y during the oscillations. Determine A, the amplitude, B, the period, C, the frequency, D, the angular frequency of the oscillations, and E, the maximum velocity. Okay, so let's look at the diagram critically. This is a meter rule, and as we all know that a meter rule is supposed to be 1 meter long. That is why they call it meter rule, meaning a meter. A meter means 1 meter. So this is a meter rule. And a meter rule, which is 1 meter long, is also 100 centimeter long. A meter rule is 100 centimeter long. So as you can see, we have 0 to 100, from here to here, 0 to 100, or even from here to here, that's 0 to 100, okay? But what we have here, we are told that these particle, this is a particle here, this is a particle, this one that is looking like a bulb, a pendulum bulb. So this particle oscillates between x and what? And y. Now, I believe you can relate this to a spiral spring and to a simple pendulum. Did you remember this diagram? For a simple pendulum, this diagram, so that if here is A and here is B, here is C, this is the equilibrium position. This particular one, this bulb will oscillate between where? Between A and what? And B. It's going to oscillate between A and B. So as you know that from A to B is half of a complete oscillation. From A to B is what? Half of a complete oscillation, as I have taught us before. Then back from B to A will now give you a complete oscillation. If you move from A to B, that's to. Then from B to A back, that's fro. So to and fro is going to give us a complete oscillation. If I also use a spiral spring, which is being displaced, if there's a mass on this spiral spring, let me assume it's being displaced from here. This is where it was before, and it's being displaced. Please go and rewatch my diagrams, or this original length, then if a mass is hanging on it, it stretches it, so that this level here is what I call the equilibrium what? Equilibrium position. Then if it is now stretched further by your hand, if you place your hand on this mass, then you stretch downward. You stretch downward. Let me draw this line. You stretch downward below the equilibrium position C. So you stretch it to point A. Now, when you stretch it to point A and you release it, what happens? It goes up and what? And down. It goes up and what? And down. So let me assume this is the maximum point where it is being displaced upward from the equilibrium what? Position. This is from C to A is the maximum downward displacement, which is our amplitude. Then from C to B is also what? Maximum upward displacement, which is also our what? Amplitude. So C to A is amplitude. C to B is also what? Amplitude. And there's no way this mass will go below point A. There's no way. Even during oscillation, it must not go below point A and it must not go above point B. So this one is very related. This question is very related to spiral spring. Very related to this spiral spring oscillation. Such that we have our oscillation from X to what? To Y. So X to Y will be to, and Y to X will be what? Fro. Now, anytime you want to deal with question like this, you must know where your equilibrium position is. What did I say? Your equilibrium position, which is center C. So I believe you know that the equilibrium position must be in between, that's X and Y. The midpoint between X and what? And Y, between X, Y. And the midpoint is going to be around here. And somebody should tell me, what do you think the midpoint is going to be? If X is 20 centimeter and Y is 60 centimeter, so what do you think the equilibrium position, which is the center of oscillation, is going to be? What centimeter is it going to be? Is it 50? Is it 30? Or is it 10? Here is 20, while here is 60 centimeter. Okay, guess what it's going to be? I believe you guessed right. So here is going to be 40 centimeter, although it is not given to us in the question. So solution. So here is going to be 40 centimeter. Now, we are told that the particle takes 4.0 seconds to move from X to Y during the oscillation, and we have to determine the amplitude. I think let us leave this 4 seconds first. Let's go to the amplitude. So A, what do you think the amplitude is going to be? I want to hear from us. You can solve even before I give you the answer. You can decide to solve before I give you the answers. So the amplitude is what again? What is the definition of amplitude, please? Amplitude can be defined as the maximum displacement from the equilibrium position. So since 40 centimeter is the equilibrium position, so you can take your amplitude to be from the center here. Let me call it a C now, please. Let me call it a C. So your amplitude is either you say CY or you say CX. Anyone. Because CY must be equal to CX. CY is maximum downward displacement, while CX is the maximum upward displacement. So what do you think CY is? From 40 to 60, that is what? 20 centimeter. And then also from 40 to 20, that is what? Also 20 centimeter. That is good. So amplitude of oscillation, which is A, amplitude A is what? You can say 60 minus 40, which is 20 centimeter, but you have to convert to meter. So A is therefore 20 over 100. That's 0.2 meter. Very simple, right? Good. Very simple. Okay. The next question, question B, says determine the period. Now, what is period again? You must get yourself acquainted with the definitions I gave to you in the first video. So, what is the definition of period? Period is the time taken to complete one what? One oscillation. Time taken for one complete oscillation. And you must know what a complete oscillation is. A complete oscillation is to and fro, to and fro. So maybe you put your hand here and you displace upward to point X. So we are going to displace our particle from the equilibrium position. So from C you displace to point X because we are told that the particle oscillates from between that's from X to Y. So you displace to point X and you release it. The moment you release it at point X, it goes down to point Y, that's to. Then it goes back again from Y to what? Up to point X, that's what? Fro. So XY, YX, that's complete oscillation. But we are told that the particle takes 4.0 seconds to move from X to Y. So from X to Y, I believe you know, that is how many oscillations? That's what fraction of complete oscillation do we have from X to Y? That's half of a complete oscillation. So if the particle can take 4 seconds for half of a complete oscillation, so what do you think is going to be the time taken for complete oscillation? That's twice of the time taken to travel from X to Y, isn't it? So I believe you can guess what the answer is. What's the answer? Answer is 4 times 2. So period T is 2 times what? 4, which is 8.0 seconds. That's it. C. We are asked to find the frequency of oscillation. Frequency. Then what is the definition of frequency again? You should be able to define that, please, by now. Frequency of oscillation can be defined as the number of oscillation that is completed in 1 second, which is the reciprocal of period. So frequency F will be equal to 1 over T, and therefore F equals 1 over 8. So plus, what is 1 over 8? 1 over 8 is going to give us 0.125 Hertz. So that's the frequency. Then part D of the question says the angular frequency of the oscillations. Now for your information, the angular frequency is also known as the angular velocity, which is what? What's the symbol for that? That's omega. So some textbooks will call it angular frequency, while some other will call it angular velocity. So the two can be used interchangeably. They mean the same thing. So angular frequency, which is omega, angular frequency, which is omega. What's the formula for omega? That's 2. You know, we have different formulas, but you have to look for the formula that is related to the quantities we already have here. The quantities given to us. So omega is 2 pi f. Okay? So omega will be equal to 2 times pi is 3.142. That's a constant. Then times f, 0.125. So we multiply those figures. 2 times 3.142 times 0.125. That's 0.7855. Then what's the unit of angular frequency? That's radian per seconds. That's good. Then E, we're asked to find the maximum velocity. So what's the formula for maximum velocity? V, maximum velocity V equals what? That's V max equals omega times what? Times R, or you say V max equals to omega times what? Times A. So since we use A in part A of the question there, and what is A? That's the amplitude. So V max, which is the maximum velocity, will be equal to, what's our omega? Let's transfer 0.7855 times, what's our amplitude? That's 0.2. So if you multiply the two, you're going to have 0.1571. Then the unit is what? Meter per second. Please don't ever forget to put your units when you are in exam hall. Don't ever forget to put your unit. Then we go to the next question. I believe we are getting what I am doing. Please, in case you have not watched my first 3 videos, do so. Go and watch them so that you'll be able to follow what I'm doing. Go and watch my first 3 videos, part 1, part 2, and part 3 on simple harmonic motion. Question number 2 says, a toy cat of mass 250 grams is placed on a frictionless, that should be a smooth horizontal track. Then a spring with a spring constant of 9.0 Newton per meter is attached between the cat and a rigid support, a rigid point at one end of the track. Full stop. When in equilibrium, the cat is at rest 10 centimeter from that end of the track. If the cat is displaced 4.5 centimeter from its equilibrium position, determine A, the period at which it oxidates. B, its maximum speed. And C, its speed when it is 14 centimeter from the end of the track. So there's the question. A toy card of mass 250 grams is placed on a frictionless horizontal table, horizontal track. So, assuming this is a track, this is horizontal. We are told the track is horizontal. Then the mass of cat, let's interpret what we have there. Mass of cat is 250 grams. Please convert to kilogram. That's going to be 0.25 kg. Okay? Now, if you can remember the saying that you don't put the cart before the horse, you put the horse before the cart so that the horse is the one that will drag the cart. You can relate with that, right? Okay. So we have a toy cart here that has to be dragged by something. Although I don't think we have anything like horse here. So your hand will be the one that will draw the cart this time around. So your hand becomes the horse that drives the cart. But we are told that a spring with a spring constant of 9.09 meter Newton per meter, is attached between the cart and a rigid support at one end of the track. So let me assume these are the ends of the track, end A and B. So these two ends are the ends of the track. So that a spring with a spring constant of 9.0 Newton per meter is attached between the cart and the rigid point at one end of the track. Now that rigid point is at one end of the track. So let me pick end A as that point where we have our rigid support. This is the rigid support. Rigid support. Okay? So that we are told that a spring is attached between the cart, okay, and the rigid support. So if this is the spring, this is the spring. The spring is in between the cart. So this is the cart. In between the cart, this cart, and the rigid support. This is the rigid support, this is the cart, this is the spring in between. Now, begin to imagine what you are trying to do here. You know, this cart can be drawn by your hand, can be drawn so that it's going to stretch this spring. So this is the spring. So that if you stretch it this way, and that's going to be displacement. You displace it. If you release it, it can oscillate to and fro freely on the frictionless track. This is a track. Okay? Frictionless track. Now, we are told that the force constant of this spring. What is force constant? According to what I taught you the other time, from Hooke's law, that's F equals KE. Force constant is K, right? Force constant of the spring. K is equal to 9.0 Newton per meter. So the question says, when in equilibrium, the cart is at rest 10 centimeters from that end of the track. At rest, that's at equilibrium. Now they are talking about the equilibrium position, since they mentioned when in what? In equilibrium. That's when the cart is in equilibrium position. And don't forget that it is at equilibrium position that an oscillating or a vibrating object is going to be at what? At rest. At equilibrium position. Okay? So they say, sorry, please. I just made a mistake here. I just made a mistake with my statement. Let me retract my statement. Let me retract my statement, please. When in equilibrium, the cart is at rest 10 centimeter. Yes, I think I'm correct. I'm correct with my statement. When in equilibrium, the cart is at rest 10 centimeter from that end of the track. So this one end, that's from end A. This cart is at equilibrium. So meaning this cart now is at equilibrium 10 centimeter. This 10 centimeter from end A. So from ear to ear, that's from ear to ear is the 10 centimeter. So we are using ear to ear as our equilibrium position from point A to this point here. So meaning I can call here point what? Point C. So my statement is very correct, very correct. So equilibrium position, the card is at rest. It has not been displaced. Okay? Now if the card is displaced 4.5 centimeter from its equilibrium position. Now, what do you think? What do you suggest that 4.5 centimeter is now? What do you suggest it is? That's what? The maximum displacement, which is the amplitude. All right. So let me convert this one to meter first. That's going to be 0.1 meter. Okay. Now we displace it. So if you displace this to what? You displace it 4.5 centimeter from its equilibrium position. That's from here now. Is there any need to draw another diagram? There's no need. So our displacement, which is our amplitude, maximum displacement. So you draw it from here to here. 4.5 centimeter. Amplitude now, A, is 4.5 centimeter. Maybe I should just draw another small diagram here. So this, we have something like this now. So that this has been displaced. Now formally here is 10 centimeter. 10 centimeter, which is the equilibrium position. Now we now have displacement, 4.5 centimeter. Don't forget here is C, here is A, and then this end and B. So should I call it D now? So how do you think this cat is going to oscillate? The cat will oscillate about the equilibrium what? Position C. So from here to here is amplitude. These are amplitude. So that amplitude is 0.045 meter. So you've displaced it. If you release it now, what will happen? It will now begin to oscillate about here. So it will be compressed this way, 4.5 centimeter from what? Where? From C. So when it moves 4.5 centimeter from C to the left hand side, maybe to point E. So this should be 4.5. From E to C, 4.5. Then back again, 4.5 centimeter again. To what? To point D. So this is going to be to and what? And fro. So from D, it will move to point E. Then back from E again, it will move fro to point D. So the amplitude is 4.5 centimeter, 0.045 meter. So we are to determine the period at which it oscillates. The period at which it oscillates. So question A, what's the period? Period T. Now, from all the values we have here, which formula do you think is going to be suitable to calculate period? Which formula is that? Do you have any formula relating to amplitude for period? What of K? What of M? Okay. Now, there's a formula that says T equals to 2 pi root. Now, I'm trying to remember T equals 2 pi root L over G. You remember how I compared this formula to another formula the other time? This constant, acceleration due to gravity is constant. So it means this is going to be M over what? Over K. Our constant is down, which is our force constant. Here it is our acceleration due to gravity that is a constant. So to easily remember this formula, that's what I do. Because at times, even the formulas I derive myself, I can't remember them, everything. There are many formulas in physics, so I can't remember everything. So there are ways I can easily remember some of those formulas without even deriving. So I can at times compare them to the ones that are very common. Okay? I know my mass and I know my force constant, so just substitute. 2 times pi is 3.142, then root m. That your m must be in kg, that's 0.25 over what? Over k. What is k? 9. So t is going to be 6.284 times root 9, 0.25, 0.25 divided by 9. That's 0.0278. T will be equal to 6.284 times 0.1667, and finally T will be thus 1.047 seconds. So that's the period. Now we are also asked to find the maximum speed. So B, maximum speed, which is V max. What's maximum speed? V max equals omega times what? Times A. Omega times A. Now, do we know omega? No. But I think we can calculate omega here now. We can get our omega from here. So omega is what? Remember this formula? 2 pi what? Pi f, or you say 2 pi over t. So since we have t here, so V max will now be 2 pi over what? Over t times A, which is now, what's 2 pi? 2 times 3.142 over t, which is the period, 1.047 times amplitude. Now you see the reason why I look for the amplitude first, 0.045. So if I simplify this, 6.284, 6.284 times 0.045 by 1.047. So this is going to give me 0.27 meter per second. So this is answer. 0.27 meter per second. Now the next question says its speed when it is 14 centimeter from the end of the track. That's from this end of the track. From this end of the track, what is the speed when it is now drawn 14 centimeter? Now, if you check this diagram very well, you will notice, let me clean here so that we are going to solve the next question here. You will notice that where we have our maximum displacement, the total length from this end A is going to be 10 plus 4.5, which is 14.5 centimeter, which is more than this displacement from where? From end A. I told you that maximum displacement, there's no way you are going to have any other displacement that is more than your maximum displacement, which is the amplitude, right? So you must not have a question that will ask you to find anything at a displacement more than what? 14.5. So we have 14 centimeter from where? From here, which is going to be around here. Around here. Now that 14 centimeter from the end A, not from the equilibrium position, please, is from end A. That 14 centimeter is going to give us what distance? What distance are we going to have from the equilibrium position? So that's what you must ask yourself. So because your distance must always be from where? Equilibrium position. Your x must be from your equilibrium position. So equilibrium position is 10 centimeter from NA. So 14 centimeter definitely will be what? It's going to be 4 centimeter. That's 14 minus 10. So we have 4 centimeter from the equilibrium position. So C, 14 centimeter from end A gives 4 centimeter from the equilibrium position. That is x equals 4 centimeter. And 4 centimeter is what? 0.04 meter. Okay? So we are asked to calculate the speed when we have a displacement of 0.04 meter from the equilibrium position. That is the interpretation of this question. So this formula comes in V equals omega into, that's omega root a square minus what? Minus x square. I believe you have not forgotten this formula. Okay? So what is our omega again? V will now be equal to, oh God, I've cleaned this and I can't remember. Okay, I will have to rewrite again, sorry. And I didn't want to waste our time. So this is 2 times 3.142 over please, I'm sorry for that. I'm supposed to substitute directly, but I've cleaned. My mass 0.25 K9 square root times 6.284. That's 1.0473 and times the root. What's A? 0.045 squared, then minus, what is X? 0.04 squared. So V will be 6 0. This is going to be 0.002025 123 minus 0.00 0.0016. V equals 6 times square root of 0.0004251234. V equals 6 times 0.0206 and V equals 0.1237 approximately meter per second. So that's the answer. So I think I've done justice to simple harmonic motion. So go to your textbooks, go to your past questions, go and solve as many questions as possible on your own to be able to build capacity in simple harmonic motion. For you to be able to stand your ground in any topic, in sciences, especially when it comes to topics that deals with calculation, you should be able to solve as many questions as possible on your own. That's to test yourself out. So please solve as many questions as possible. Thank you. So please don't forget to subscribe to my channel, like, comment, and share with your friends so that they can benefit from what is happening on this channel. Thank you and goodbye.